In section 3.2, we're going to look at the derivatives of exponential functions. So in this section, we're going to compute derivatives of exponential functions, and we're going to explain the significance of the constant e. So let's go for our big rule here, and that is the derivative of a to the x. We need a to be greater than 0 here. For a constant greater than 0, the derivative will be natural log of a times a to the x. And note that natural log of a is a constant. So you have some kind of constant times a to the x. And then in particular, we have this really nice rule that if a is the special number e, then we have that the derivative of e to the x using the rule above is natural log of e times e to the x, but natural log of e is just equal to 1. So this whole thing is just e to the x. And the note at the bottom kind of explains why this is important. E is a very special number in mathematics. It's used all over the place. It's found all over the place. And one definition of e could be that it is the exact number that when you take the derivative of the number to the x power, you get the same function back. And the only other function that gives you the exact same function back when you take the derivative is 0. Those are the only two functions that have that special property. And that's going to mean that taking the derivative of e to the x is going to be one of the nicest things that we do in this course. And we're going to use this function all the time and into Calc 2 and Calc 3 as well. So let's explore this constant e a little bit more. When we introduced limits, when we did it numerically, that is, we plugged in values closer and closer to the special value to find what number it's approaching, we looked at the limit of x approaching 0 of 1 plus x to the 1 over x power. And it's a weird function, and we kind of found that when you plug in numbers closer and closer to 0, it seems to approach this special value of e. And note that this is actually another definition of the value of e, is that it is equal to that limit. And that limit is very important, and it shows up almost exactly in a lot of different applications, least of which is something like the compound interest formula, continuous compound interest formula. We're going to explore another limit, and that's this limit down here. 1 is equal to the limit as x approaches 0 of e to the x minus 1 over x. I just want to take a little bit of time to show where does that limit come from, because it comes from that definition of e. This is also a good example of how we can kind of do some algebra with limits. So we're going to do some of this in this chapter. So I'm going to rewrite this limit as a limit down below. I'm going to start with the limit, and then what I'm going to do is I am going to say that without the limit there, 1 plus x to the 1 over x is going to be close to e as long as x is close to 0. And that's what the limit is saying. It's just how close to 0 do we need to be exact. So then with this approximation, I'm going to do some algebra. I'm going to take both sides to the x power. And then I have 1 plus x is going to be about e to the x for small x, when x is close to 0. Then I'm going to subtract 1 off of both sides, and I get x is about e to the x minus 1 for small x. Then I'm going to divide by x on both sides, and I get 1 is about e to the x minus 1 over x for small x, for x close to 0. And then I can bring the limit back in, because for small x means let's let x get as small as possible, and then these are going to be exactly equal. All right, so we're going to use this limit that we just came up with on the next page. So now let's do the proof of the exponential derivative. So this is going to be another proof that you are not going to be responsible for. You're not going to have to replicate this proof at any point, but it's good to kind of see where it comes from and to see that this isn't just a magical formula that pops up out of nowhere, that there's a reason for it. So let's go through the steps of this. We start with the limit definition of the derivative, and note that that's how we're going to start almost all of these proofs. So using this, the function is a to the x. When I plug in x plus h into the a to the x, I have a to the x plus h. I'm then going to do an exponent rule. Note that if you have x to the a plus b power, that's the same as x to the a times x to the b. So I'm going to rewrite that as a to the x times a to the h. Then I have an a to the x in both terms in the numerator, so I'm going to factor that out, and I'm left with a to the h minus 1. So then the next thing is a little bit weird, and that is I can take this a to the x and bring it out in front of the limit. And why can I do that? Because in terms of h, which is what the limit is in terms of, a to the x is a constant. There's no h in that a to the x expression, so I have no problem bringing it in front of the limit. The limit doesn't affect it at all. And then I'm left with limit of a to the h minus 1 over h. To deal with that limit, we're going to do another weird trick, and that's going to be to rewrite a as e to the natural log of a. This is a weird thing to do. We're seemingly making it more complicated. This is what's known as the log trick, that you can rewrite a as e to the natural log of a because e and natural log are inverse functions. And by doing this, we're going to be able to bring in our limit that we did on the previous page. So rewriting a as e to the natural log of a, and then noting that if you have x to the a to the b power, that's x to the a times b, we can rewrite e to the natural log of a to the h as e to the natural log of a times h. And now we have this weird limit. So the last big algebra rule we're going to do is that if I have t equals the natural log of a times h, I'm going to do a substitution here. I'm going to replace natural log of a times h with t. And note that that means that h is going to be t over the natural log of a. I can just divide by natural log of a on both sides. Let's remember that natural log of a is just a number. All right, in order for this to work, if I'm going to change the limit to be in terms of t instead of h, because that's what I'm trying to do, I need to make sure that they both approach the same number. So as h approaches 0, t is also going to approach 0 just because we're multiplying by some kind of constant. And that's not going to change where we're going. So I'm going to replace everything with t instead of h, and I have a to the x, limit of h approaches 0, e to the natural log a h minus 1 over h. I'm going to replace natural log of a h with t, and I'm going to replace h with t natural log of a, and I'm going to replace h with t just because they're both approaching the same value. Now we do a little bit of algebra. I can bring a 1 over natural log of a out of the denominator, which is just going to be a natural log of a total, and I'm left with this limit, which we found was equal to 1 on the previous page, where I have t instead of x there. And then I am left with the answer, which is that this derivative is a to the x times natural log of a. So once again, this is a more complicated proof than we did in the last few videos. And you are not responsible for replicating this, but I think it's important that you understand how we get from one step to the other. It's important to know how to do these algebraic steps. There's some exponent rules. There's a fact about inverse functions. And we're doing a nice substitution, which we're going to do in the future as well, that helps us deal with the limit.